Right. In section 2.3, we talked about measures of center. In section 2.4, we're going to talk about measures of variation. So instead of trying to describe the center of the data, we're going to describe how spread out a data set is. The two most basic measures of variation are range and deviation. Range is just the difference between the maximum and minimum data entries. Super simple to compute, but because it only uses two pieces of data, it doesn't represent the trends in the overall data very well. So, deviation is the first measure that we'll meet that actually does take into account multiple pieces of data. And the deviation is just the difference between each data entry and the mean of the data set. And you can see we're using that Greek letter mu again to be the mean of a population. So to calculate the deviation, you literally just take the piece of data minus the mean. And the sum of the deviations of any data set should always turn out to be 0. So keeping these things in mind, let's look at our first example. I modified this to do only part of the example from the book. So I'm working with the data from one corporation that hired 10 graduates. The starting salaries for each graduate are shown. Find the range and the deviation. So in order to find the range, we have to take the max score and subtract the min. Now, please note that this is salary in thousands of dollars, okay? If you were only paid a salary of $41, that'd be pretty sad. So I'm going to scan these numbers, and it looks to me like 47 was the max. And the lowest would have to be one of these in the 30s. It looks like 37. So when I do the maximum, I'm going to remember that this is in thousands. And I subtract the minimum, which is 37,000. So the range turns out to be $10,000. Okay, and it's important to put the units on it and to represent the amount accurately. 10 would not be the correct answer here. Now for the deviation, we have to calculate the distance that each piece of data is from the mean. All right, in order to calculate the deviation, you have to subtract the mean from each piece of data. So the first thing I need to know is the mean. So what I need to do is add up all of these salaries. The mean is found by adding up all of the salaries and dividing it by the total number of salaries in my data set. So I'm going to sum up the x's, and that turns out to be, I believe, 415. And then that would mean to find the mean, I'm going to take 415, I'm going to divide it by 10, and that gives me a mean of 41.5. And again, that's in thousands of dollars. I'll put the units back on once I finish the problem. So now to calculate the deviation, I take the value, the first one being 41, I subtract the mean, and I get a negative deviation. I get negative 0.5, which tells me that the first salary, 41,000, is $500 less than the mean. I'm going to continue subtracting all the way down the table and get my deviations. Right, so those are the deviations. So at this point, we've finished what the question asked us to do. However, we do want to remember that these deviations are in thousands of dollars, so it's good to put a label on it. And the temptation might be to try and total the deviations to get a sense of how the data as a whole is behaving. But as the note up above told us, when you sum up the deviations, which is the x minus mu's, you get 0. So deviation speaks about how far an individual piece of data is from the mean, but in terms of trying to get an aggregate for the whole data set, we can't just simply sum those up. For that reason, we have other measures of variation. So we're going to begin by looking at the population variance and the population standard deviation. So for population variance, it is defined to be this, okay, according to this formula. We've got this little, what looks like an O with a tail across the top. That is the lowercase letter sigma in the Greek alphabet. And it has a 2 on it. It's squared because the population variance, instead of just totaling the population, what we do is we take all the individual variances and square them, because squaring a number gets rid of the negative signs, and therefore all the numbers are positive. So when you total them up, you won't get 0. So we're going to square the variances, we're going to add them up, and we're going to divide them by the total number of pieces of data, which for a population is capital N. But here's the only problem. Because we introduced this squaring in the formula, the units on the population variance would be squared too, which is weird. So the population variance would be measured in thousands of dollars squared for the last example. I don't really know what that means. So to overcome this, we usually take the square root of the variance, which is called the standard deviation. And that's what the next box says to you. We have the exact same formula that's up above, and we just put a giant square root over it. When we do that, we get just sigma. So that is the symbol for population standard deviation equals the square root of the sum of the variances squared divided by capital N. What standard deviation will do is give us an idea of how all the data is spread out from the mean. The more spread out it is, the higher the standard deviation will be. So the steps to calculating the standard deviation, honestly, when I do it, I just look at the formula and I say, okay, I've got to take each piece of data, subtract the mean, then I need to square that, then I need to total that, then I need to divide that by capital N, then I take the square root. But for those of you who don't like the symbols and notation as much, this is the whole process spelled out for you in everyday English. So the steps that we're going to follow are these 6. So we are now going to go back to that data set with salary in thousands and find the population variance and standard deviation. All right, step 1 is again to find the mean, and we already did that part. We found that the sum of the pieces of data was 415, and we calculated our mu by doing the sum of the pieces of data divided by number of pieces of data, and we got 41.5. The next thing that you would do would be to calculate your deviations, taking the piece of data, subtracting the mean. We already did this, so I'm just going to bring those numbers over. All right, now that that's finished, I am ready to do the next step. We found the mean, we found the deviation. I am now supposed to square each deviation. So this next column will represent the x minus mu pieces of data squared. So in other words, to get the first value, I'm going to take this negative 0.5, I'm going to square it and put the result over here. That will end up being, and again, all these numbers should turn positive because a negative times a negative is positive. So my first value will be 0.25. I'm going to go ahead and go down this column, squaring every single entry. All right, so all the numbers have now become positive, and keep in mind each of these numbers contains information about how far a piece of data is from the mean. For instance, 47 is the furthest from the mean, and so you see the largest number. We're now going to go ahead and total this column. Now, I prefer just using the notation sigma and that I'm summing up the squared variances, and you should get 88.5. Just so that you know, your textbook introduces weird notation here for the squared sum, and it calls it SS and has a little X subscript. That's what they're writing instead of the sigma notation, but I don't know. I just find that confusing. So when you see that in the book, it just means the sum of the squares for the pieces of data. All right, so we squared the deviations, we added up the squared deviations, and now we're ready to divide that by capital N. So I'm going to take my sum of my squared deviations, divide by capital N. So I'm going to have 88.5 divided by 10 pieces of data. So at this point, what we've computed is known as the population variance, okay, which is denoted with the little sigma with a squared on it. And when you calculate that, you would get 8.85. And keep in mind that's in thousands. So really that number represents 8,850 dollars squared, which again is just weird. So therefore we do one last step. We take the square root of the population variance, which gives us just little sigma. So I take the square root of 8.85, and again, this is where you'll want to have a calculator that has the square root button on it. The final answer that I came up with is 2.97489. Okay, it keeps going for a bit. So a word about giving answers here. The general rule we're going to go with is to give one more decimal place than the original data. So our original data did not have any decimal places to it. So the most I should be reporting in this answer is 1 decimal place. And if you round, it's not going to be 2.9 because the number after the 9 is bigger than 5. This is going to round off to 3.0. And please remember that that actually represents a standard deviation of $3,000. That's the value for sigma. Now, by itself, that doesn't really tell you a lot, but when you have a second data set, it's a really good way to compare. Oh, this one has a larger standard deviation. I know the data is more spread out. So it's most useful when you can compare it to another data set.